1.5, we're talking about slopes of secants and average rate of change. So just quickly, can anyone tell me what a secant line is?
It touches something, but it doesn't go through it.
Okay, on the right track. That's a tangent line.
Oh,
So
okay.
secant is the other one. So you're right. Let's say,
Intersections.
yeah, let's say you have a curve. Then the secant line is a line that will intersect the curve at two spots. Okay, so this is a secant line. And when we're talking about rate of change, we're actually going to be talking about slope of the secant line. Okay, how are we going to do that? Well, we have 2 points of intersection, which means we have a change in y, and we have a change in x, and we can calculate the rise over run. We can calculate the slope, which corresponds to the rate of change. Now, before we get into all that trivia, what are some things that we can measure and the measurement can fluctuate? So what are some things that you measure where the measurement will fluctuate? Will change over time. Time, like it goes to 12 or 24 and then down. Yeah, down to 0 again. That's kind of true, yeah. Yeah, time.
Sunlight.
Yeah, sunlight, that's a good one. Yep. Hours of sunlight per day, like throughout the year kind of thing. Yeah.
I see you're trying to avoid these sharp edges that are hard to.
Yeah, I don't think they so much apply to what we're talking about. What about tides? The height of the tide every 12-ish hours. Yeah. All right, you kind of get it. So the rate of change, so these things are changing, right? It's a change. The tide is, it's high and low tide, high tide, low tide, high tide, okay? Now the rate at which they change can be calculated by having a secant line and finding the slope of that secant line.
So that's just the change over time between those 2 points.
Correct.
Okay.
That's the rate of change. All right, let's take some notes. You must, yes. Okay, on your page there, you have some space for notes, and we're going to be talking about rate of change. A rate of change is a measure of the change in one quantity. A rate of change is a measure of the change in one quantity with respect to the change in another quantity. A rate of change is a measure of the change in one quantity with respect to the change in another quantity. What is that saying? Well, if we take one of our examples, as time goes on, the temperature goes up and down. So as time changes, the temperature will also change. Okay? That's all we're saying. And in this case, it would create some kind of curve. Now, the one quantity depends on the other quantity. Okay? So you have a dependent variable and an independent variable. Okay, it's the change in one quantity with respect to the change in another quantity. You can have, or this is how we kind of say it. I'm going to leave that drawing there. You can use it or not. It's your choice. The rate at which y changes with respect to x. Okay, it's a good way to remember rate of change. The rate at which y changes with respect to x. The rate at which, in this case, temperature changes with respect to time. Okay, or we could use h for that. All right, there are two types of change. We can talk about average change and instantaneous change. Say instantaneous first. Instantaneous ROC. Instantaneous rate of change is basically the rate of change at an exact spot. So that would be the slope of a tangent line. Okay? We don't have the math necessary to figure that out. Okay? What we're going to talk more specifically about is average rate of change. Average rate of change. This is change that takes place over an interval. Whereas we could write a little jot note for instant rate of change is change.
Are we ever doing instant rate of change in this course?
Not in this course. Change that takes place in an instant. Now, again, we will only have the math tools in order to calculate average rate of change, but we can get our average rate of change to approach instantaneous rate of change simply by making our interval smaller and smaller and smaller. Okay? So here, if we were to consider that secant line, we would be getting the average rate of change in that interval. Okay? Well, what happens if we make this interval smaller and smaller and smaller by bringing point 2 closer to point A? Well, we get closer and closer and closer to the instantaneous rate of change at point A. Does that make sense?
Yeah.
In order to figure out the instantaneous rate of change, you need calculus.
Oh, sick.
So when you get to calculus, you'll be able to figure that out. Okay? So next semester, that's what we'll be looking at. Yeah, it's not difficult, really. It's just a different math. All right, so you have a picture right below. Yeah, you have a picture that kind of looks like this. Something like that. Yeah? So notes beside that picture. The average rate of change, ROC, between 2 points corresponds to the slope of the secant. The average rate of change between 2 points corresponds to the slope of the secant between those 2 points. For example, the average rate of change of y, and I'll just draw my axes somewhere there so you can see that we're on the coordinate plane. Change the color of my line. Okay, the average rate of change of y with respect to x between the points P1 and P2 is determined by the slope of that line. How do we find the slope? Well, if you know what P1 is, it has coordinates x1, y1. And if you know where P2 is, it has coordinates x2, y2. Okay? And then the average rate of change looks like this. We say delta y over delta x. Delta is just a Greek letter that means change. So it's the change or difference. Difference in y over the difference in x. That's the change in y over the change in x. It's going to start to look pretty familiar. So here's how we say it. Change in y over change in x. Well, how do we figure out the change in y? We simply figure out the difference between our two y coordinates. So we've got y2 minus y1 in the numerator, and the change in x is the horizontal change between P1 and P2. That's x2 minus x1, which, as you can see, this is just the formula for slope. The slope of a line when you know 2 points. Okay, example 1 is a really easy look at it. It's not a curve or anything really confusing. It's just interpreting average rate of change by looking at this graph. So the graph represents the amount of money in a bank account over a 1-year period. And you have it there in front of you. You can see where it starts. You can see where it is at the end of 1 year. You can see where it is at the end of half of the months. There's different intervals there where things are happening. So all we're going to do is discuss what it says. The question is, how much money was in the account at the start of the year? That's you guys.
It is 500.
500 bucks. Okay. How much money is in the account at the end of the year?
200.
Good. So now we have our base, our beginning, and our end. Now we want to know about the average rate of change during different intervals. Okay. So the first interval that we're going to talk about is months 0 to 5. How does it change? Can you describe that line or the trend?
I do 0 to subtract 5 months. What does that mean?
0 to 5. Months 0 to 5. Yeah?
Oh. Well, we hit up at 10,000. No, 1,000.
Okay, so you can say how much it goes up by. What else can you say about it, about this trend? What did I draw? What is here?
The line is 100 per month. Oh, that's rate of change.
Rate of change will be about 100 per month.
There's also the slope, 100 x, I guess.
Okay. It's a line, right? It's a line, so it has constant growth. So the rate of change is constant. Notice how you can use those words in the same sentence. It's a rate of change. This corresponds to the slope of this line, but the slope is constant. The slope is not changing. If it were changing, it would be a curve. Then the rate of change is changing. Here, the rate of change is constant. Okay? So between 0 and 5 months, it's a line with positive slope. And I'm going to use a different color. Line with positive slope. Line with positive slope. Therefore, average rate of change is constant and increasing. Constant and, not increasing. Don't use that word. That's the wrong word. Constant and positive. Which, if we're interpreting it, that means it's going up by the same amount of money each month. Okay? Let's look at our next interval. We're going to look at the months 5 to 8. And what's happening?
Literally nothing. Rate of change is 0/3, so just 0.
Okay, so we would describe the line just by looking at the graph. It's a horizontal line. Horizontal line, pardon?
It's a constant.
So the amount is constant, which means the rate of change is 0. Okay, average rate of change is 0. So the amount doesn't change, is how we would interpret that. Last little piece here, months 8 to 12. We've got a steep negative slope, okay? Negative slope, line with negative slope, which tells us that the average rate of change, it's a straight line, so it's constant, and it's negative. Constant and negative. It's decreasing. The amount of money in the account is decreasing by the same amount from month to month. In part C, you guys don't have, it doesn't indicate what A, B, and C is it? Okay. So part C, you have space off to the side. I am going to slide over. I have a little bit of space. I'll do it over here. Part C, we're asked to determine average ROC for each interval. Okay? So again, the first interval, months 0 to 5. In order to determine the average rate of change, I'll write it out for the first one. Average ROC equals, well, in this case, what are the two quantities that we are comparing that are changing with respect to each other? What's changing? What's changing along the x-axis? Can't be sleeping yet. You have a whole period to go through. What's changing along the y-axis?
Alright, x-axis we have negative 800.
Well, let's talk about our variables here. So we're moving horizontally. That's time. What's the y-axis represent? The vertical axis?
Okay. We're on the third segment, right?
Amount. Thanks. Amount measured in dollars. So over here we have average rate of change is going to be the change in amount over the change in time. So for the months from 0 to 5, we're going to take 5 minus 0 in the denominator, because that's our independent variable. And we can see, so basically we're going from this point to this point, right? So up here, what is the amount at the top there? Is it 1,000? 6, yeah. We've got 5, comma 1,000. So at the top we have, in the numerator, we have 1,000 minus 500. If we simplify that, we get 500 over 5. We get average rate of change of 100, which tells us that the amount of money in the account is increasing on average by $100 per month. Now in this case, the whole line is straight, so the average rate of change is constant over this whole section. But let's say your money was actually doing something like this, which is more realistic, even more probably like this if it's an investment. Okay? Then you could pick this second point And you could say, well, I don't know what it's doing specifically at all these other intervals, but over this period of time, on average, I increased $100 a month. Okay? We're just going to do one more. We'll do interval 2, which was from 5 months to 8 months. So our average ROC, okay, is delta A over delta T, the change in amount over change in time. Change in time here is from 8 to 5. And in the numerator, your amount is from 1,000 to 1,000. Well, 1,000 minus 1,000 is 0. 0 over anything is 0. What does that tell us? The amount stays constant. No change occurs. Okay, rate of change in this case is 0. And then the next one, you would end up with a negative rate of change. Okay, you'd end up with a rate of change. I'll just write down the sentence and then the answer. So you've got delta A over delta T, and you end up with negative 200 if you do the calculations for this last section from 8 to 12 months. Okay. The amount in the account is decreasing on average by $200 per month. In this case, the slope and the rate of change is the exact same in each interval, and it's constant in each interval. Okay, let's get slightly more challenging here and work with a curve in our next example. So in example 2, we're going to calculate and interpret the average rate of change from a table of values. Okay, so we have a problem that is posed to us. We have a population of bacteria that is on a surface, and we have a new antibacterial spray that's being tested on that bacterial culture. The table shows the population, P, of the bacterial culture T minutes after the spray is applied. So 0 minutes after the spray is applied, as in right when it's applied or just before it's applied, the population is 800. 1 minute later, you've killed off 1. This might be in the thousands or something like that, but either way, your population is decreasing, and it's decreasing according to that curve that you see next door in the screen. So what we're going to do is ask a few questions. A says, how can you tell that the average rate of change is negative by examining either the table or the picture?
Well, it goes down, like you can see over time. I don't know how you would say that.
Yep, that's okay. Negative rate of change in a table. Numbers, I should say values, will decrease. What about in a graph? How can you tell that it's negative? Yeah, the slope of any secant will be negative. Okay, that's just quickly how to look at things that are negative. So what we're going to do is determine the average rate of change of the number of bacteria over the entire time period, and then interpret this value. So B, determine average ROC for entire time period. Then interpret. How would we determine the average rate of change for the entire time period? Well, we simply go average ROC. We use our formula. It's the change in the dependent variable, which is population, over the change in the independent variable, which is time. And we're doing the whole time period. So that means we're going all the way from 0 minutes to 7 minutes. So in the top, in the numerator, we're looking at our population. We're going to take y2, which is 37. And we're going to subtract y1, which in this case is 800. And in the denominator, you're going from 0 minutes to 7 minutes. So you're going to take y2 or x2, which is 7, take away 0. Okay, in the denominator, 7 minus 0 is the whole time period. It's 7 minutes. And in the numerator, you have 37 minus 800. Should hear some clicking on your calculators. It's negative 763. And then we quickly divide that. You can divide that one in your head. 700 divided by 7 is 100, and 63 divided by 7 is 9. So you're looking at negative 109. So let's interpret that. What does that actually tell us?
Is rate of change of negative 109 bacteria per minute.
Over the whole 7-minute period,
Yeah.
right? Over 7 minutes, the number of bacteria decreases on average by 109 per minute. Now, does it actually kill 109 bacteria every minute? No. But over the whole scheme of things, if you divide it all by 7 and get the average, then it looks like 109 per minute, okay? Just to kind of go back up here for a second, we want to, should indicate that the points that we used, points from table that we used were 0, 800, and 737.
Can I go to the
Yeah.
Thanks.
Okay, we're going to look at a couple of other intervals. We're going to do the first 3 minutes and the last 3 minutes. Okay, so in C, we're going to find the average rate of change for first 3 min. And then over here, we'll find it for the last 3 minutes. So the first thing we're going to want to do is take our points, the points that we're using. So from the first 3 minutes, we're going from 0, 800 to 3 and its partner, 737. In the last 3 minutes, 7 take away 3 is 4. So we're going from 4, whose dependent variable population is 652, to the end of 7 minutes where the population is 37. And again, we're just going to calculate the average rate of change over those 2 intervals. So the first 3 minutes, average rate of change is the change in the population with respect to the change in time. Change in population, I take my second population value, 737, subtract my first one, which is 800. Time, denominator, take my second value, which is 3, subtract my first value, which is 0, and we end up with negative 63 over 3, which reduces to negative 21. So in the first 3 minutes, the average rate of change is only 21 bacteria per minute. You could write a little sentence. We're going to skip that part so we can carry on. Over here in the last 3 minutes, kind of in your head, you can make a prediction of what might happen. but change in population over change in time. Again, sub in our values. There's a lot more change happening here. The time interval in the denominator is the same. It's still 3 minutes. And the numerator, 37 minus 652, negative 615. You can divide that by 3. You end up with negative 205. So at the end, it's decreasing much more rapidly at an average of 205 bacteria per minute over the last 3 minutes. Okay, how can we tell? Just discussion. How can we tell? We have a table, we have a picture of a graph, and now we have calculation of rate of change for the first 3 minutes and last 3 minutes. How can we tell that the rate of change is not constant? Yeah, the rate of change in the first 3 minutes is different than the rate of change in the last 3 minutes. There's a clear answer. It's not constant. Okay? Judging by the picture, well, the average rate of change, if it corresponds to the slope of a secant, the slope of the line up here is different than the slope of the line down here. It's different than the slope of the line here. Okay? It's constantly changing. The rate of change is constantly changing. And from the table, the population column, if I can just kind of scoot random notes in here that you don't actually need to take, but let's say you had the population column, the difference, the first difference between these is not constant. Okay, it goes down by 1, then it goes down by 17, then it goes down by 45. Okay, it's not constant. So that's how you can tell. Okay, last example, example 3, calculate and interpret average rate of change from an equation. The equation is here. We have a football kicked into the air. A football is kicked into the air. Its height, comma, h, measured in meters, after t seconds is h with respect to t equals negative 4.9 t squared plus 14t plus 1. Okay, so that is the graph that you have drawn for you there. Football is kicked into the air. It goes up and then down over time.
A second function under that.
All right, what are we going to do? We are going to
plug in the x for a and b.
Well, we're going to determine average rate of change over, first we're going to do through the interval from 0 to 0.5 inclusive, and then we're going to do from 2 to 2.5 inclusive. Now notice this is not coordinates of t and h or of x and y. This is just talking about t values. Okay, we're going t from 0 seconds to 0.5 seconds after the ball is kicked, and from 2 seconds to 2.5 seconds after the ball is kicked. Okay, so right at the beginning and close to the end of when it lands. So you should have a good idea of what this average rate of change is going to look like. Any predictions on how we could describe that? You can cheat and look at the picture if you want. But right when you kick a ball,
It's going to be close to 6, but a bit under.
it's going to be a whole number, a big kind of whole number. It's growing, it's changing quite quickly with respect to time. The height is increasing most rapidly right at the beginning, positive number. Okay, what about really close to the end when the ball is about to hit the ground?
It's going to be negative.
It's going to be negative, and it's going to be it's going to be dropping more and more rapidly, right? So it's going to be a whole number again, but a negative number. Okay, whereas at the top, if you did like at 1.5 seconds, then the rate of change might be a little bit more gentle, less slope. Okay, here we go. So for our first interval here, from 0 seconds to 0.5 seconds, we are missing information still. We need the change of height over the change in time. We have the t values, we don't have the h values yet. So step 1 is we need to find corresponding h values. All right, so h of 0, when t is 0, what is h? Well, we sub in 0 for all of this. I'm only going to do this. I'm not going to do this for every step because, well, I guess I have to. Subbing in 0 is the only really easy one. Wherever I see a t, I'm going to sub in a 0 so that this becomes 0, this becomes 0, and all I have is 1. So basically the initial height of the ball is 1 meter above the ground. What about for h at 0.5? That means everywhere I see a t in the equation, I'm going to sub in a 0.5 in order to find out what the height of the ball is at 0.5 seconds.
Alright, this doesn't make sense. That makes sense.
You can put this whole stretch in your calculator. Okay, 0.5 squared is 0.25. Half of 14 is 7, plus 8 plus 1 is 8, and subtract that from it. I'm just going to write it down what the book has. So we've got 6.775. So basically after half a second after the ball is kicked, it's already almost 7 meters in the air. Okay, whereas it started at 1 meter, which means the kicker is kicking it out of his hand. Okay, so now we have some corresponding values, and we could find the average rate of change here. So the average rate of change is equal to the change in h over the change in t, which is 6.775 minus 1 for the change in height, and the change in time is 0.5 minus 0. All right, so we have 5.775 over 0.5, which basically means 5.775 times 2, which your calculators can do, and you can do, 11.55. Let's give ourselves a little statement. The average rate of change of the height of the football from 0 seconds to 0.5 seconds is 11.55 meters per second. We're going to do the same thing on the other side. I'm going to do it much more quickly. We're going to find the corresponding h values for our t values that are given at the beginning of the interval and the end of the interval. So here we go. H of t, we're going to sub in 2, sorry, h of 2, we're going to sub in 2 wherever we see a t. That is, click, 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 9.4. Then we're going to find out the height of the ball at 2.5 seconds, which means I'm going to sub in 2.5. into our equation everywhere we see a t?
The answer is 5.375.
5.375. Now we can get our average rate of change, which again is delta H over delta T. Sub in our values. We're going 5.375 subtract 9.4. You can see how that's going to be a negative value. And we're going 2.5 minus 2. We're going to have a negative over a positive, which is going to result in a negative slope. And reduced, that ends up being negative 8.05. Therefore, average rate of change from 2 seconds to 2.5 seconds after kick is decreasing, or we can just use negative, is negative 8.05 meters per second. Okay, and then in your picture you have the two secant lines drawn. You have a secant line from A, B, and you have a secant line C, D, and those obviously correspond to the first half a second and the time interval from 2 seconds to 2.5 seconds, which is the height is decreasing at the end, it's increasing at the beginning. Not much else to say there. Average rate of change corresponds to the slope of the secant line between 2 points that you pick or that are given for you. Okay, practice problems. Page 62, numbers 1, 5, 7, 12.